Okay. So last time we introduced the sheaf of Kähler differentials. Omega x for an algebraic variety x. This sheaf was defined as the quotient of the diagonal ideal modulo this ideal squared, and it was coherent. OX module, and in case X was affine, the global sections of this sheaf was the module of Kähler differentials. So it was K of X module, and maybe let us compute it in the simplest example. When X is the affine space and dimensional, and we will essentially use the fact that this is an algebraic group, just the additive group to the power n, and due to this fact, it's possible to compute the ideal of diagonal very explicitly. Namely, we have this diagonal, well, delta an inside an times an, and this is just the kernel of the difference. From GAN times GAN to GAN. Right, we have the multiplication morphism from algebraic group to itself. In this case, this multiplication is just addition, and two vectors are equal if their difference is 0, right? So in other words, there is an isomorphism from AN times AN, some transvection isomorphism, where X and Y goes to X and X plus Y. And this isomorphism takes, let's call it T because it's transvection, T of AN times 0 is just the diagonal, right? And hence, we can easily compute this ideal of diagonal. So T of the ideal of AN times 0 is the ideal of diagonal. And the ideal of IN times 0 is just the functions on the first copy times the ideal of the origin in the second copy. Okay, but the ideal of the origin in the second copy is just the maximal ideal. We know its generators; they are just the usual coordinates, and so hence the quotient model of the square is just a free model, just the vector space with generators x1 and so on, xn, just a vector space, n-dimensional vector space. And this means that the desired Kähler differentials module is just a free model over the polynomial algebra. With generators, the differentials of coordinates dx1 and so on, dxn.
Okay. Как в этой конструкции t участвует вот в последнем утверждении?
Well, this t is only needed to compute explicitly the diagonal, the ideal of functions vanishing on the diagonal. Yeah, it's just the product of well, it's the image under t of the product of all functions and the functions vanishing at the origin of the second copy, right? Okay, and then in the home exercise, in the home assignment, the first exercise, you have to check that the RAM differential is what it's supposed to be. So it takes any polynomial, and then you compute its partial derivatives and multiply by the differentials dxi. Okay. So this simple algebraic recipe reproduces the usual analytic formula. Okay. So last time we started with some basic properties of the RAM differential. Say in the affine case. And these were first the constants were annihilated by the RAM differential. Then we had additivity. And multiplicativity, that is just the Leibniz rule. Then we proved that the Kähler differentials are generated by differentials of functions as a model over functions. Okay, and the last property we're going to prove right now is as follows. It's some universality property, very useful. We will use it today for the whole day. It's a universality of the RAM differential. So suppose we are given any module over the ring of functions, and we are given a morphism delta from the ring of functions to this module, satisfying the basic properties A and B. That is different. Well, the delta of constants is delta annihilates the constants and satisfies additivity and Leibniz rule conditions. And then there is a unique morphism L from Kähler differentials to M, such that our delta is the composition of L and the ramp differential. Okay, so Keller differentials, they are a solution of some problem, and for this reason they are somehow well defined, uniquely defined. They are natural. Okay, so let's prove this.
А можно вопрос?
Yes. Yes.
Как мы определяем этот D? Вы говорили, что это какая-то разность.
All right. Yes, absolutely. It was well. Give from there are two projections from x squared to x, the left and right projections. Now given a function f on x, you can lift it to x squared either via first projection or via second projection, right? And then you can take the difference. This difference will vanish on the diagonal, so it will lie in the diagonal, and then just take its value modulo the square of this ideal of diagonal. Okay.
Okay, спасибо.
This was the definition of the ramp differential. So now let's prove this property. And we don't have to care about uniqueness, because we know that the Keller differentials are generated by the differentials of functions. So if you know how your morphism behaves on differential of functions, then it's already defined on all the Keller differentials. Okay, so we only have to check the existence.
Не совсем понял, почему вот из C следует единственность? Еще раз, может?
Because if you still remember what we're proving, this universality property in D, we are given this delta on functions, okay, and we know that the Keller differentials are generated by differentials of functions. So if you know on differentials of functions, then you know it everywhere. And now we prove the existence, and by the very first property that the constants are annihilated, we see that this differential delta from functions to our module is k-linear. And now we extended to morphism nabla from the functions on the square just by k of x linearity in the second variable. Okay, and it means that nabla of the sum fi of x1 times gi of x2 is the sum of gi of x, the second variable, yeah, times delta of fi.
I think we have tensor product there.
Tensor product, yeah, isn't it written? I think it's written tensor product.
Yeah, but nabla of sum of fi tensor gi.
Oh, okay. Here you mean, yeah?
Yeah.
That's what you meant. Thank you. Thank you. Okay. And then we have some basic properties of this nabla. I mean, the idea is to somehow to copy the construction of the Durham differential. Yeah, as I just told Daniil, this Durham differential arises from some map of functions on the square on an x square. Yeah, so that's what we're trying to mimic. We get some map from function on the square, and then from this we'll produce the desired map. Well, so we'll restrict it to the ideal and then model ideal squared, and we'll obtain the desired map from scalar differentials to M. So the properties are very similar. First, nabla of f if it's a function just of the first variable, independent of the second variable, this is just delta f. That's clear by construction. Also, well, maybe let's call it I. The second property is that nabla of f of x2 is 0, just because we extended by linearity. Then nabla of f of xy plus g of xy is the sum of nablas, additivity.
Для чего мы сейчас ввели вот это дельта?
Well, we're trying to construct this universal map L from scalar differentials to the module. And since scalar differentials are constructed via functions on the x square, we are using this nabla on x square plus nabla g of xy, and finally, sort of Leibniz rule, nabla of.
I'm sorry, you mean
Yeah.
that x is equal to x1 and y is equal to x2, isn't it?
There is no. Here. Yes.
Okay, thank you.
Yes, let me rewrite it. X1, X2, X1, X2, X1, X2. Equals f of x1 times nabla g of x1 x2 plus g of x1 times nabla f of x1 x2. Okay. Now again, as so now nabla satisfies all the basic properties the same as the Durham differential, yeah, and with the same consequences. In particular, it implies that nabla of the square of the diagonal ideal is 0, and hence.
А почему в правиле Лейбница вот последнему у нас точки для f совпали, например, x1, x1? Можете напомнить?
No, maybe you can check it yourself. I think it's very straightforward. So we know this, and well, this means that nabla induces a map L, just as the desired, from I modulo I squared. This is just our scalar differentials to M. That's good. Also, sorry. Also, we know that nabla f of x1 minus f of x2 is delta f, and hence this L is compatible. So L of df is delta f, and there we are. Okay, that's what we wanted to prove. Okay. So once again, the Keller differentials, they do have some explicit description, but they solve a universal problem. Okay, so for this reason, they are natural, and we will now exploit this naturality consequences. Like this. So again, maybe let's have let's work in the local situations so that we have two affine varieties. So we'll have a morphism from x to y, and these are affine varieties. And then it induces the morphism between the squares, f times f from x times x to y times y, and it takes diagonal to diagonal. Delta x goes to delta y, certainly. So then the pullback of functions takes the diagonal ideal on y to diagonal ideal on x, and the squares also to squares. So it induces morphism from Keller differentials on y to Keller differentials on x. Okay, and it is linear over y. So the pullback over some function a on y times the differential form is the pullback of a function times pullback of the form. So it's k of y linearity. And also there is a compatibility with differentials. Namely, if you take the differential upstairs on x of pullback of some function, then it's the same as you first differentiated on the base, and then pull back the result like this. So it's for any function on the base on y. Okay, and hopefully you will remember this from the basic calculus, and it works here as well. Okay, and so by this linearity, this pullback induces a k of x linear morphism that I will denote df upper star from the differentials on scalar differentials on y with scalar extended to x, to functions on x, to scalar differentials on x. Okay, and again, from the point of view of basic calculus, this is just dual to the differentiation. Yeah, you have a morphism from x to y, so it induces at each point the differential on tangent spaces, and there is a dual, just transposed map on the cotangent spaces. And in the family, this dual differential on cotangent spaces forms just this morphism we just described. Okay, and now we will apply it to the case of closed embedding. Yes, so how maybe it was useful to imagine x as a sort of vibration over y, but now it's an opposite situation. Say x is a closed subvariety in the affine space, and we already know the sheaf of not the sheaf, the model of differentials, scalar differentials on the affine space. Okay, and now using this pullback, the co-differential, we can use it to compute, at least in some cases, the scalar differentials on affine varieties. Maybe even more generally. So let's suppose we have a closed embedding of two affine varieties. Say z in x, a closed affine subvariety. Okay, and then say let j in the functions on x be the defining ideal of z. So the function is vanishing on z. And then the claim is that we have an exact sequence of models over z as follows. So we have the ideal of z modulate square. That is somewhat similar to the definition of scalar differentials. Yes, if z was diagonal in x squared, yeah, it would be just the definition of scalar differentials. And then there is some differential going to scalar differentials on x tensor functions on z. So we just restrict differentials on x to z. Yeah, if you somehow geometrically view differentials on x as sections of some vector bundle on x, yeah, then you just restrict this vector bundle to z. And from here you have the codifferential, as we just defined above, to the scalar differentials on z. And this is surjective. Okay, but I do not claim that the differential on the left is injective. Okay, and this differential on the left is just defined by the evident formula. D of A is differential in the sense of x, tensor 1, for any function in this ideal. Okay, so let's prove that there is such an exact sequence.
Можно вопрос?
Yes.
Что все-таки делает D и со звездочкой? Он как будто бы посылает форму умножить на функцию, берет pullback, как будто бы. Да?
Oh yeah, yeah. You just so in well, maybe geometrically. Let me comment. Sorry. So in case when everything is smooth, so recall that omega of x was the global sections of x with coefficients in this sheaf of Dirac differentials, and omega x is the sheaf of local sections of the cotangent vector bundle which is denoted like this. Okay, you know there is a tangent bundle and there's a dual vector bundle, cotangent vector bundle. Okay, and then well, I have to turn the page, unfortunately. So we have this cotangent vector bundle on X. Okay, and we can restrict this to Z. Okay, Z is a subvariety in X, so we can restrict any vector bundle on X to Z. Fine, and then there is this projection to the cotangent bundle on Z, and it's called the codifferential of the closed embedding. Okay, and this is surjection, and in the kernel you will obtain some other vector bundle on Z, and this is called the cotangent vector bundle. Sorry, conormal vector bundle, TZX star, and in fact this will be an embedding. Okay, this conormal vector bundle. Okay, but in this smooth case, it's an embedding. In general, it's not necessarily an embedding, but there is just a sequence like this. Okay, did I answer your question, Daniel?
Ну, у меня, может быть, попроще был вопрос. То есть это D со звездочкой, он просто берет форму умножить тензорную на функцию и выдает, применяет все, к этому всему применить просто pullback.
Yeah, just restrict to Z, yes.
Ага. Понятно.
Did I answer now?
Yes.
Oh, great.
So in fact,
Yes.
it is not a differential.
Well,
course.
well, it is. It's a codifferential. You restrict forms on X to forms on Z. It is codifferential. It is dual to the natural map on the tangent bundles, and on the tangent bundles, it is really the differential of your embedding.
Ah, okay. Speaking about embedding, but
here we are only considering the closed embedding from Z to X. Yes.
Oh, but up to the page we see just usual F, just a map from x to
Then
y.
this F, yes, and is an arbitrary map. In particular, it could be a closed embedding. So
Yes,
now we're
but
considering
if
the
it is
particular
not,
case of closed embedding. If it's
Okay,
not,
okay, but-
it's always it is always a codifferential. There's always
okay.
dual to differential on tangent vector.
Okay.
Okay. Fine. So let's prove this. So we have to check many properties, but almost all of them are evident. Namely, in the right hand side, this codifferential is surjective. Since the restriction on functions from k of x to k of z is surjective. It's a closed embedding of affine varieties. And the Keller differentials, say, of z is generated by the differentials of functions okay, it was one of our basic properties. Fine. Now, it was say first point. The second point is that the pullback of the ramp differential of function on x is the ramp differential on z of the pullback of this function, and this is 0 if a lies in the ideal. J is the ideal defining z inside x, right? This means that the restriction of the differentials of this ideal is 0, and hence the composition of this codifferential with the first differential from the ideal to differentials on z is 0. Okay. This is 0. Now, by the Leibniz rule, we have the differential of the square of this ideal lies in this ideal, well, times Keller differentials on x, and hence this D induces homomorphism, linear over k of x modulo this ideal, that is k of z, from the ideal modulate square to the differentials on x restricted to z. Okay, so now everything is checked except for the exactness measure. Okay, it remains check the exactness in the middle. Okay, so let's consider the middle homology. So M is scalar differentials on X restricted to Z. Modulo the image of J modulo J squared. Okay, and we have a map from this M to different scalar differentials on Z, and we have to check that this map is an isomorphism. And to prove that this is an isomorphism, we will just explicitly construct the inverse morphism. L from scalar differentials on Z to M. Okay, and how do we construct the inverse morphism? Just by the universality, right? You remember we started today by proving the universality property of scalar differentials. So in order to construct a morphism from scalar differentials to somewhere, we have to construct an analog of the RAM differential. Okay, so by universality, property of scalar differentials, we have to construct a differential delta from functions on Z to M. Okay, and then this will give rise to the desired L, and then we'll check that it's inverse to small m here. Okay, so let's take a function on Z and lift it to a function a prime on X. Now we have an enclosed embedding of affine varieties, so the map on functions is surjective. Then the RAM differential of this lift on X modulo the RAM differential of the ideal J is determined by A itself, so it does not depend on the choice of our lifting. So we set delta of A is this class. Of dx of A prime, and this class is in M. M is exactly the quotient as you see modulo differentials of J. Okay, so now this delta from functions on Z to M satisfies the basic rules. I mean, it's additive, satisfies Leibniz rule, kill the constants, and so on. And hence we obtain the desired map L from differentials on Z to M, such that the composition L with differential on Z is our delta. Okay. Now we have this naturality property that dz of I star A was equal to I star of dx A, maybe A prime if you want, like this. And it implies that the composition L with M, and M is this induced map from the restriction of differentials on X to differential on Z. Yeah, this composition applied to dx of A prime is dz of A. Okay, so we proved that L is left inverse to M, and what else do we need? Maybe also need to check that L is surjective. But this is again by the basic property, since all the differentials generate M by construction, and the differential dz of A generate Kähler differentials on Z. Okay, so we proved this property. It was a long proof, yeah, more than 1 page long. So here was this property. There was a relation of Kähler differentials on a closed subvariety. So how to write them down in terms of Kähler differentials on the ambient variety. Okay, and now we apply this fact, or maybe something very similar to the case when Z is just one point in X, and then we are able to answer Sergei's question from last time, how the cotangent space, the Zariski cotangent space at a point is related to the Kähler differentials, namely that the fiber of this sheaf of Kähler differentials is nothing but the Zariski cotangent space at the point. Okay, so let's prove this. Omega f and the cotangent space at any point. So So the proposition is that the fiber at any point equals the cotangent space at this point. Okay. So
А вот можно спросить?
yes.
Вот тут вот геометрический слой имеется, да, то, что называется? Ну, в литературе пишут
I'm not sure.
geometric fiber.
Maybe I forgot. Maybe it's called geometric fiber, but it's just the fiber of a sheaf. Namely, but by definition, for any sheaf F, this fiber. Well, sorry. F sub x is F modulo the maximal ideal of this point. Okay, and there is some notation clash with the stocks, the germs, but here I mean the fiber.
А вот тут вот не нужно взять f на каком-то открытом множестве, содержащем точку x.
No.
Вы так написали f
It's a sheaf of modules over the sheaf of, or the structure sheaf of rings. So no, you don't need anything else.
Ну, под mx понимается пучок, да? Пучок небоскреб.
Mx is just the maximal ideal. You take the localization of the structure sheaf at this point. So this is the stock, or sometimes they say germ of the structure sheaf.
Do you mean f modulo mx times f?
Oh yes,
Because
yes, yeah, that's understood. Yes, of the structure sheaf O at x. Okay.
Спасибо.
Welcome. Okay, so let's now, maybe the notation now is more clear, and let's go on with the proof. So what do we want to prove? We want to prove that we take well, again, x, it's a local question, so we can assume that x is affine, and then we take the global sections, the module of Kähler differentials, and then we take its fiber. So we just change the scalars. So we would quotient out by the maximal ideal, and we want to prove that this is isomorphic to m modulo m squared. Okay. Now, my notation is not very consistent, because at the previous page I said that this m was the maximal ideal in the local ring, right? And now I take the maximal ideal in the global ring, but it doesn't really matter. So maybe you can, if you want, you can define it by some other letter, but now at this page, mx is a maximal ideal in the global ring k of x. But once again, that doesn't really matter which definition of maximal ideal you take. We already
But
discussed
it depends
it.
of point, yes?
Oh yes, certainly. Yes, it's a max, m sub x.
Okay.
Yes. Okay. So if you remember from the last year when we started studying Zariski tangent and Zariski cotangent spaces, we had the notion of local differential at a point dx from all the functions to this Zariski cotangent space. Maximal ideal moduli squared. Namely, it was defined the same way. So you take any function, and then it takes some value at point x, and f of x. Oh, sorry. It's just f minus the value f of x. Okay, f of x is just a number in the base field k. So you subtract from your function this value. Now it vanishes at point x. So it lies in the maximal ideal, and you take the class of this difference. Okay, but this was the definition of dx that we gave in December. Okay, and again, it satisfies the standard basic properties like Leibniz rule, additivity, and like this. Okay, so we get by universality a kx linear map L from scalar differentials to the Zariski cotangent space such that dx f equals L of df. By df, I mean the ramp differential on big X. Okay. Now m times mx times mx modulo mx squared is 0, and hence L gives rise to L bar, just a vector space k linear map from the fiber of the scalar differentials to the Zariski cotangent space, like this, and this L bar has the property that dx f is L bar of df tensor 1. Okay, and we were almost done. So we constructed the map in one direction, and now we want to prove that it's an isomorphism. So we have to construct some inverse map, and again, the inverse will be constructed by universality property. So to say conversely, we have a morphism from functions to scalar differentials. Again, with taking fiber at point x, it takes f to df tensor 1, And this morphism satisfies the standard basic properties, and hence we get a linear map say M from mx modulo mx squared to the fiber of scalar differentials. Such that the composition M and dxf equals df tensor 1. Okay.
У тебя там фактор mx или mx квадрат?
Oh, sorry. Yes, thank you. Just model mx. Sorry. And now clearly M and L are inverse to each other. Okay, so we used the universality of the global differentials, scalar differentials on x, and the local differential and at the point x. Okay, from these two universal things, we produced maps into opposite directions. Okay, so now we're able to prove a nice corollary, namely that the set of smooth points x in x, say, let's call it x smooth, is open in the Zariski topology and dense. If you remember, in the last lecture of the last year, we finished by proving that any variety has a smooth point. Yes, and now we prove something much stronger. We prove that not only there exists one smooth point, but almost all points are smooth. So first of all, last time we proved that if a point is smooth, then it lies on just one irreducible component. Yeah, any point in the intersection of two or more irreducible components is necessarily a singular point. So a smooth point must lie on just one irreducible component of x. So we may assume x irreducible of dimension say d, and then we just by definition X is smooth if the dimension of Zariski tangent space, that is the same as dimension of Zariski cotangent space, is the same as dimension of the ambient variety X, that is D. Okay, but we know that in principle it can be bigger. But now we have a coherent sheaf omega X such that the Zariski cotangent space at X is just the fiber of this coherent sheaf at X. Okay, but again, if you remember from the last December, we proved that the function on X given by dimension of the fiber of a coherent sheaf is upper semi-continuous. I mean, it can only jump. Yeah, it's generically constant, and then if your point specializes somewhere, it can only jump. So by the last year theorem, the set of points X such that the dimension of the fiber is less than or equal to dimension to D, or to arbitrary number, but say D, is open. So there we are. Hence, X smooth is open. And again, by the last theorem of the last year, X smooth is non-empty, hence it is dense. In X. Okay, there we are. Fine. Now the next thing is another explicit computation of the sheaf of differentials, but not in the affine case, but in the projective case, namely for projective space. So sort of explicit computation of the Kähler differentials of projective space. So you see, since it's not an affine variety, you cannot describe it by global section. And in fact, well, maybe you will see soon that there are no global sections at all. There are no global differential one forms on the project space. So definitely not the way to describe the global sections, and instead we'll describe it as a certain subsheaf of another explicit sheaf. So we'll use the projection as always from an+1 without the origin to Pn. It's denoted by pi, and then we will have we do have the pullback pi star from the Kähler differentials on Pn to Kähler differentials on A n plus 1, but without the origin. Now it's certainly it is an embedding, and we can describe somehow we can describe the image. So this pi is a torsor with respect to the multiplicative group, which we used many times already. So the desired sheaf of differentials is a subsheaf in the direct image of differentials on the punctured affine space. Namely, these are GM invariant sections. Okay. So in functions of degree 0. Maybe I'll write it down like this. In invariant sections. So the invariant sections are just maybe we can write it down in this form. So they are differentials of the coordinates, and the coordinates with respect to this multiplicative group action, they have weight 1, right? They are linear. So under the dilations, they have weight 1, and so to have weight 0, we have to multiply by the functions of weight -1, and they form the line bundle note like this. Okay. So in other words, our task is to specify the Kähler differentials of projective space inside this guy. Okay, so this is just the line bundle OP n of -1 to the power n plus 1. Okay, and inside there we are going to specify our vector bundle of Kähler differential. So you see the projective space is covered by the usual charts. Any chart is isomorphic to the affine space AN. And in the beginning of today's class, we described the Kähler differentials on the affine space AN. So locally, this sheaf of Kähler differentials is just locally free and n-dimensional vector, well, sheaf of sections of n-dimensional vector bundle. Okay, and we have just embedded this n-dimensional vector bundle into another n plus 1 dimensional vector bundle. Okay, and well, we are going to specify it as a kernel of a certain function. So the theorem.
Извините, а как вы погрузили вот этот пучок дифференциалов в push-forward? Какой-то сопряженностью тут, наверное,
Oh, yes,
очевидно использовали?
Yes, certainly it lies in the push forward of its own pullback. Yes, I can go up and down. Yes, certainly.
Надо будет подумать.
Yeah.
А GM торсор это значит что? Какая-то терминология.
There's an action of the multiplicative group on the punctured affine space, and it's a free action, and the quotient model of this free action is just the projective space Pn. Okay.
GMM торсором называется AN без нуля. Или...
Yes, the punctured affine space is a GM torsor, and being a GM torsor means that the action of GM is free, and there is a projection to the base. In this case, this base is Ppn, so that GM acts on the fibers of this projection, and on each fiber, there is a free transitive action. Okay, so that the base identifies with the quotient of the total space.
Спасибо.
Okay? So there is an embedding into this direct sum. And in the quotient, you just get the structure sheaf. Okay, and well, let me say, how do you get this morphism alpha to the structure sheaf? It's very simple. If you take differential of a coordinate and multiply it with some section, then it's just the product xi times this section sigma. Okay, and the section xi has degree 1. So sorry, this xi as the function coordinate has degree 1. The section has degree -1 because it's O of -1. And so their product has degree 0, so it's just a function as stated. Okay, so let's prove this. So the action, the dilation action of the multiplicative group on the punctured affine space gives rise to the action of its Lie algebra. It's just one-dimensional, so it's just one vector field, and this is the Euler vector field. E, and this is the sum from 0 to n, xi d over dxi. Okay, on the punctured affine space, and since our forms are pulled back from the quotient model of this action, they are orthogonal to this vector field. And in fact, this is the only condition. We just wanted to have one condition. Remember, our Kähler differentials have rank n. We embedded them into some vector bundle of rank n+1. So we need just one condition to specify this image. And this condition is just the orthogonality to this particular vector field. So all the forms pulled back from from the project space are orthogonal to this vector field E. Okay, and that means the scalar product of our form and this E is 0. But what is this scalar product? If omega is the sum of fi dxi, then the scalar product of omega and e is just the sum of xi fi. Right, and that's what we claimed. So we are done. Okay, and this is a very important calculation. And just let me formulate one last corollary of this. So I can consider the canonical line bundle. By definition, this is omega, small omega Pn. This is the top exterior power, namely nth exterior power of the Kähler differentials. So you know, in the basic calculus, you don't only have the first differential forms. You have a higher degree differential forms as well. Yeah, namely they are exterior powers of the first degree differential forms, and in particular have the top exterior power that is the volume forms. Okay. So these are called the canonical line bundle in algebraic geometry, and in this case, it is isomorphic to O minus n minus 1, OPN minus n minus 1. Yeah, just from this exact sequence, because the top exterior power is multiplicative in exact sequences, right? And OPN has trivial. It's a trivial line bundles, so its top exterior power is also trivial, and we get this isomorphism. In particular, say omega p1 is already one-dimensional, so it's the same as the canonical line bundle, and it's O p1 of -2. And in particular, you see that at least here there are no global sections at all, right? O p1 of -2 that doesn't have any global sections, so there are no global Kähler differentials on p1. Okay.
Could you please once again explain how the exterior power functor behaves in exact sequences? Because I don't believe that that it is just that it maps exact sequences to exact sequences.
Oh, no, by no means. So if you have a rank D vector bundle, say E on X, then you associate to it its top exterior power. It's called the determinant E. This is just the top exterior power. Okay, and then the claim I made is that if you have an exact sequence, then there is a canonical isomorphism. The determinant of the middle term is the determinant of the left term, tensor determinant of the right term. Okay, and well, you choose this locally, and it glues up globally. Okay, so are there any other questions?
А вот про сечение от минус единицы на проективном пространстве, там же нету глобальных сечений.
Absolutely, no section.
Вот, а вы говорите, возьмем сечение, значит, и как бы вы имеете в виду локально, да, возьмем
Oh, certainly,
сечение
yeah.
степени минус 1.
When I yeah, when I spoke of sections here, it was about local sections.
Мгм. Да. Хорошо.
Okay. So if we have no other questions, then I'm saving today's notes. Oops. I'm stopping the recording.